Hey, good evening, class. Tonight I'll be talking about chromatography. The following is the outline of discussion for our topic tonight. First, I'm going to discuss about chromatography as a separation technique. I'll be defining the terms mobile phase and stationary phase, and I will give some examples of chromatographic techniques such as paper chromatography, thin layer chromatography, column chromatography, high performance liquid chromatography, and gas chromatography. And finally, I will introduce to you chromatography as an analytical technique. So, we will be talking about terms like retention factor, retention time, external standard method, and spiking. First and foremost, chromatography is a modern separation technique that is based on the interaction of the analyte to the mobile phase and stationary phase. Consider the following GIF image shown. What is done in this image is that the sample is spotted around here and a solvent solution is placed right here. So this is a typical paper chromatography setup where the sample is spotted on top of the paper and is partially submerged on a solvent solution. So this solvent will travel upwards the paper and will push this analyte. So this analyte is a mixture of other components. So what happens afterwards is that as the paper is inserted in a solvent saturated chamber, the solvent will travel a particular distance around here and the analyte along with the other components also move upwards. So this movement is based on the interaction of the analyte to the mobile phase and the stationary phase. In this context, the mobile phase is the solvent, whereas the stationary phase is the paper. The essence of chromatography lies in the interaction of your analyte to the mobile phase and stationary phase. So how does the analyte interact with the mobile phase and stationary phase is the cornerstone of chromatography. So in this case, the stationary phase is a polar molecule. So since it's made up of paper and paper is made up of cellulose, and cellulose is a polar molecule. And if the analyte is also a polar compound, then the analyte interacts with the stationary phase. So as you can see here, in the following photo, suppose compound A is our analyte and we have a mixture of other components. So we could say that analyte is strongly attracted to the stationary phase compared to compound D, for the reason that compound D travels very far compared to compound A. This is the starting line. One of the most relevant analogy for this is, suppose you are walking along with your friends, this is you, and you're walking along with your friends, and along the way you see someone you like, and your friend also sees someone he or she likes. So what happens here is that since you like this person at this point, so you have A, B, C. So B tends to stay a little longer compared to A and C. And as A and C moves along here, along this path, you have A and C. A is attracted to this. So A tends to stay a little longer compared to C. So that is one of the most relevant analogy for this. The stronger the interaction to the stationary phase, the slower the analyte moves along the paper. So that is the essence of chromatography. Some examples of chromatography are the following. We have paper chromatography. In paper chromatography, our stationary phase is paper, and paper contains cellulose as a polar molecule, and cellulose is a polar molecule. Therefore, polar analytes also interact with it, and nonpolar analyte do not interact. So as a result, polar compounds and nonpolar compounds are separated through chromatography. The mobile phase in this context is solvent. Another one is we have thin layer chromatography or TLC. TLC has the same, actually all chromatographic techniques has the same fundamental principle. the interaction of the analyte to the mobile phase and stationary phase. In this context, we have a sample matrix made up of analyte and some other components, and as they are submerged in a solvent saturated chamber, the solvent will move upwards and the analyte together with the other components will be separated. So suppose we have this one as our analyte, meaning the other ones are other components of the mixture. So in this case, our stationary phase is the LC plate, and the LC plate is made up of silica gel. So silica gel is also a polar molecule. Our mobile phase is also solvent. Another example we have here is column chromatography. Okay, column chromatography has stationary phase and mobile phase. So what is done here is that a sample is injected here, is placed here, and we have the stationary phase which is made up of silica gel. And afterwards, solvent is poured on top of this, and the solvent will push the analyte and the other sample components downwards, and this will cause a separation. So the strongly attracted molecules tend to retain longer than the weakly attracted molecules. So after some time, the molecules that are weakly attracted to the stationary phase are eluted first. So these are, for example, this one is component A, and this one is our analyte B. So A is eluted first, and finally, upon successive addition of solvent, our analyte is also eluted. Okay. The stationary phase in this context is silica gel mounted in the column, and solvent is our mobile phase. Another chromatographic technique we have here is high performance liquid chromatography, or HPLC. HPLC is one of the modern analytical techniques that have been discussed previously. So the following is a diagram for HPLC. We have our solvent right here and the pump which allows the solvent to be eluted in this HPLC column. So the HPLC column is a vacuum, so it does not have any air into it. Our sample is injected around here, and as the solvent moves right here, the sample is pushed towards this HPLC column. So this HPLC column is made up of stationary phase. So it has a stationary phase. Based on the interaction of your analyte with the stationary phase and the mobile phase, the analyte might be eluted first or eluted last. Okay, suppose we have our analyte here and another component here. So it means that the analyte is strongly attracted to your stationary phase compared to the other components. So this one is component B and this one is component A, which is our analyte. After some time, component B will be eluted around here in the detector, and it will be transmitted as a signal through a personal computer. Also afterwards, our analyte will also be eluted in the detector. So the stationary phase in this context is the HPLC column, and our mobile phase is the solvent. Finally, we have gas chromatography. So gas chromatography has a similar diagram to HPLC. So instead of solvent, liquid solvent as a mobile phase, we have gas as a mobile phase. The following is the schematic diagram for GC, or gas chromatography. We have a cylinder which houses the gas that is used in gas chromatography. It is either nitrogen gas or argon gas. And this gas is connected to this sample compartment, the carrier gas flow controller, which controls the pressure of the gas, and we have sample injection chamber around here. So the sample is injected right here, and it will be pushed by the gas, which is the mobile phase, and the sample, which is made up of the analyte and some other components, goes through the column in the oven. So this is a very long coiled column, and the analyte interacts with the coating of the column and shall be eluted first or last depending on its interaction with the column. Finally, upon elution, it is it goes to the detector and shall be transmitted as data by the computer. All the chromatographic techniques essentially follows the fundamental concept of chromatography, which is interaction of your analyte with a mobile phase and stationary phase. So the column is made up of, okay, suppose this is our column. So column is coated with something, and this coating shall be interacting with the analyte. So for example, our analyte is A and we have B. So if our analyte interacts with the coating in the column, then analyte will stay much longer compared to B, which does not interact with the coating of the column. Okay, so we have learned how chromatography separates the analyte from a component mixture. But how is chromatography used as an analytical technique? First and foremost, I'd like to introduce to you the terms retention factor and retention time. So retention factor is often used in TLC and paper chromatography. So retention factor has the formula distance traveled by the component and distance traveled by the solvent. So what is done here is that, suppose this one is our analyte and this one is starting line. So this is the distance traveled by the solvent, which has a length B, and this one is a distance traveled by the analyte, which has a length A. The calculation for the RF is therefore A over B. So what does RF tell us? Retention factor tell us if the analyte is strongly attracted to the stationary phase or not. So an RF value that is greater than 0.5 means that the analyte is not strongly attracted to the stationary phase, whereas an RF value of less than 0.5 means otherwise. So the analyte here is strongly attracted to the stationary phase. The other photo shows a definite example for the calculation of RF. Okay, suppose the distance traveled by the solvent is 2.8 centimeters and the distance traveled by the analyte is 2.1 centimeters. So if you calculate this one, 2.1 divided by 2.8 is equal to 0.75. This means that the analyte is not so strongly attracted to the stationary phase. The next concept that I would like to introduce to you is the concept of retention time. This is the schematic diagram for GC or gas chromatography. So what happens in the GC is that there are components that are eluted first and there are components that are eluted last. So when we say eluted, meaning these components goes out from the column to the detector first and some other components are also eluted last. The time it takes for the analyte to be eluted to the detector or from the column is what we call the retention time. If the analyte is eluted first, meaning it is not so strongly attracted to the column, and if it is eluted last, meaning it is strongly attracted to the column. So what we often see in gas chromatography and HPLC is a chromatogram. So the chromatogram shows the retention time of different components in a component mixture. Suppose we have a sample injected here, and that sample is comprised of methanol, ethanol, 2-methylpropanol, propanone, and propan-1 all. So these are the components that are contained in our sample. Upon subjecting this one to gas chromatography, these are separated in the column. So the first component that's eluted is methanol. So the retention time is around 0.8 minutes. We have ethanol for the compounds 4, 5, and 6. So these are the compounds that are found in the chromatogram after we use gas chromatography. So the chromatogram shows us different peaks which signify different sample. So these peaks are also different samples and they have different retention time. So we could say that specific samples or specific analyte also have specific retention times. Okay, once again, the takeaway of this slide is that the greater the retention time, it means that that particular component or compound is strongly attracted to the column. It's either It's either true for column chromatography or gas chromatography. But how is chromatography used in chemical analysis? Suppose we have the following analysis. Different concentrations of methanol are subjected to column chromatography or let's say HPLC, high performance liquid chromatography. So we have 100 ppm, 200 ppm, 300 ppm, 400 and 500 ppm of methanol. Since we are talking about methanol, then they have similar retention time. Okay, so as you can see, those that has lower concentration tend to have lower peak height and peak area. So we can either choose peak height or peak area. Okay, but in chemical analysis, what is often used is peak area. Upon integration of this peak, we can determine the peak area. So suppose for 100 ppm, we have 200, 300, 400, 500. So this is the concentration of the standards. So we use a standard solution for methanol, and we have a peak area data here. Okay, suppose the peak area is 0.1, 0.2, 0.3, 0.4, and 0.5. What is done here is that we could generate an equation of the line from these two data, from the concentration of the standards and from the peak area. So we get an equation of the line equal to y is equal to mx plus b using regression analysis. So I have taught you this one when we talked about spectroscopy. So based on the equation of the line, if we subject an unknown sample into the HPLC or gas chromatography, we get a peak area. And from that particular peak area, we can calculate the concentration of our analyte. Just like in Beer's law calculations that we have performed. Another method to determine the concentration using chromatographic techniques is spiking the sample. So we have an example here. Chromatographic technique is used in the determination of an analyte in a river water sample. So what is done here is that the sample has components A and B. The concentration of components A and B are not determined, but we know what are these components. After subjecting the sample to gas chromatography or HPLC, we get this blue colored chromatogram or two peaks, blue colored peaks, this one. And since components A and B are known, what are these components? So one of the ways to determine the concentrations of components A and B is by spiking the sample. So what does spiking the sample mean? Spiking the sample means that a known concentration of components A and B are mixed along with the sample solution. Okay, once again, spiking means that a known concentration of the analyte, which is a standard, is added to the sample solution. This will cause an increase in the peak area or peak height. So how do we calculate the unknown concentration of components A and B? So we can use ratio and proportion. So peak area of the spiked sample over peak area of the unspiked sample is equal to the concentration of the standard spiked plus concentration of the analyte over concentration of the analyte. Or we could say A of spike, A of unspiked is equal to concentration of standard plus concentration of analyte over concentration of analyte. Since these components are known, then we can calculate the concentration of analyte. Let's have an example for this. Suppose the area of a spiked sample is 0.25 and the area of unspiked is 0.150. The concentration of the standard that is spiked is we have let's say we have 10 ppm and we should calculate the concentration of the analyte. Using this formula, it's just ratio and proportion. We have 0.250 over 0.150 is equal to 10 ppm plus x over x. We have 1.667 is equal to 10 ppm plus x over x. Then we have 1.667x is equal to 10 ppm plus x. And therefore we have 1.667x minus x is equal to 10 ppm. And finally, we have 0.667x is equal to 10 ppm. Divide both sides by 0.667, and we get the value of x. Okay, we have 15 ppm. Therefore, the concentration of the analyte in our sample is 15 ppm. Okay, let's have an example for this one. Okay, suppose we get an equation of the line that is equal to, after using regression analysis, we get an equation of the line that is equal to 0.1240x plus 0.025. So take note, y is the peak area, x is the concentration. So upon subjecting an unknown sample to chromatographic analysis or gas chromatography, we get a peak area of 0.150. Okay, this one is the equation of the line generated from the standard solutions using regression analysis. So substituting this one to y, we have 0.150 is equal to 0.1240x plus 0.025, and we have 0.150 minus 0.025 is equal to 0.1240x. Divide both sides by 0.1240, and we get the value of x, which is equal to 1.01. Okay, suppose this one is in ppm. Okay, so that is how we make use of chromatographic techniques in chemical analysis. That is the end of our lesson tonight.